this is yet another orthogonal direction, or sort of fairly high angle direction to the rest of the work going on in this workshop. And he comes from the tradition of probabilistic reasoning, which has existed as a separate area of AI and machine learning for many years. And he's one of the experts in that. And looking forward to your talk.
Thank you, Sanjeev. Yes, indeed. So I will start by saying this is not a talk about neural networks, but we will be learning a representation, and it will be a very interpretable one. It's actually a distribution. We will be learning from prior knowledge, and we will actually be heavy on symbolic reasoning. All of these topics came up in the panel yesterday. In fact, the different stages of the talk will lead into the final conclusion, which identifies 3 particular areas for symbolic reasoning in machine learning. So that will be the final outcome. I will be sampling results from a line of work. This particular line of work is about 2 years old, and it's mostly my group and Guy van den Broek, who's a faculty and colleague in my department. So this work is basically joined between our groups. We will be learning tractable distributions over what we call structured probability spaces. So actually, I'm going to start by explaining what that is. That is core to the whole presentation and this line of work. And I will start with a running example that we're going to use throughout. You have a department that offers 4 courses, logic, KR, probability, and AI, and you have data on what students have done. So this row, for example, says 17 students took logic and KR, but not probability and AI. And my goal is to learn distribution from this data so I can use it to reason about what students tend to do. So up until this point, this is the classical machine learning problem. The new element here is that we have what we call prior knowledge. So in addition to the classical data, we have this. In this particular case, this corresponds to program requirements and prerequisites. So the new machine learning problem here that, as far as I know, has not been formalized on books the way I'm going to formalize it here is I need to learn from both of these inputs, right? So what does that mean? If you look at this particular problem, we have 4 variables. So the traditional probability space that we're going to call the unstructured space has the 16 elements which correspond to the different combinations. But due to this prior knowledge that we have, or the constraints, the real space is actually smaller because I know upfront that 7 out of these 16 elements are impossible. I'm telling you that upfront. And then the task now is more specifically is learn a distribution over this particular structured space. This notion of constraints and a structured space is everywhere. And I'm going to show you now a number of examples from what others have done in dealing with it. The point is going to be that we're going to propose a systematic way of dealing with this. So our final goal, and what I'm going to lead you into eventually, is a new box that takes data as you know it and constraints and learn a model. Now, the key thing is going to be in the talk is what is this guy? That's going to be actually a new creature that is interesting, as you will see. And that's the mathematical task. Now, people deal with this all the time. Here's an example. And they do it in different ways. In this work, Kevin Murphy and his colleagues wanted to identify players in sports videos, and they wanted to say that a player cannot exist in multiple locations in the same frame. How did they deal with that? They actually handcrafted that into the model. So they were using HMMs, and then Kevin and his colleagues went there and basically put that in. In language, constraints are all over the place, right? You can see all kind of examples. And in this area, people have actually come up with models to deal with that. Originally with work of Dan Roth. Now, structured predictions. In a sense, what they do is they force the constraints on the output of the predictive models. But as you'll see, we're actually forcing it on the space itself. But the point is, they had to deal with this, and they had to come up with particular models to deal with issue of text, because as you can see, it's all over. Constraints everywhere. This happens to be a model that I worked with. NASA aims to develop It's just a fragment of a model of a power system. It's a classical graphical model. It's full of zeros because of constraints that corresponds to the physics of the situation. Recently, actually, the work by DeepMind on predicting routes in the underground had to deal with the same problem. If you don't know the physics, you will predict routes that do not exist. And in fact, that's what happened. And the solution they came up with is they effectively had to force that outside the neural network, right? Because how do you guarantee that you're gonna recommend routes where indeed there is a link between one location and another? So as you can see, it comes up all the time, and I just killed my screen. Okay. So people deal with this by ignoring constraints, handcrafting, using specialized distribution, all the way to basically hacking their way around it. And you can see all kind of problems with that. So again, we'll see how to deal with this systematically. Goal again is general purpose. So what I'm going to do next is just tell you a little bit about this notion of structured space, because so far it looks like it's just about physics and constraints. In fact, it's more than this. I'm going to show you now how this notion of structured space, if you can handle it, if you can build this box that I told you about, how you can systematically learn distributions over combinatorial objects like permutations, rankings, routes, in a systematic fashion. So I'll do this, and then I'll show you the actual model that we'll actually learning. So to be clear, so logic will be the language to specify this structured space. So in this particular example, instead of this, we will basically have these, and that's what we're going to use for that. Now, let me show you now. I'll show you this in detail, the next one, because it's simple, and then I'll run over the other ones more faster, which is how we can use this notion of a structured space to learn systematically distributions over combinatorial objects. So let's look at rankings, total rankings, or permutations, right? Something that has been studied extensively. In fact, people have dedicated distributions for this particular combinatorial objects, like distributions over rankings. And this is one of the particular data sets that's been out there in the literature. People have reported on 10 items. That's how many permutations, 20 items. Okay, how do we do this here? You introduce a Boolean variable, I sub j, that says item I is in location j in the total ranking. You have n square of these variables. The unstructured space is 2 to the n square. Some of these elements are permutations, some of them are not, because they actually place some items in more than one position, and they may put more than one item in a particular position. How do you get the structured space? As simple as this. You write n constraints, Boolean constraints, that say each item is assigned to a unique position. You write another n constraints that say each position is assigned a unique item. Now, if you look at these constraints, among the 2 to the n square, a bunch of them are filtered by these. You're left with the n factorial elements that correspond to permutations. Believe it or not, this is all you have to do in this framework to start learning distributions over permutations. And later I'm going to show you experimental results how this actually does better than some of the more sophisticated, dedicated distributions for permutations, right? So here we're learning a distribution over the structure space. You can do the same thing for routes. It's pretty simple. If you have, let's say, a grid, you have source, destination. You can include a Boolean variable for every edge, whether that edge is on the route or not, from the source to the destination. Here's the variable assignment, assigning true to these variables and false to the others, which corresponds to a route. Here's one that does not. Again, you can write a Boolean formula whose instantiations are precisely those that corresponds to valid routes. And now you're ready to learn distributions over routes. In fact, we've reported on this already in the literature. Now we're doing a real map of San Francisco, learning using this box to basically learn distributions. It's tractable. The output is tractable. I'm going to get to that in a second, which means that once you have that distribution, you can do things like someone's going from here to there, and they've already done this, what's the most likely path they're going to take from this to the end? Linear time. You can answer that in the representation that I haven't told you yet. You can do this, but this is very preliminary. You can do this to learn define structure spaces that corresponds to parse trees in language. It's pretty easy to induce the space of graphs, just one variable for every edge. You add a cyclistic constraints, you get trees. You can do basically go all the way to having distributions over parse trees. This is very preliminary, but again, this will allow you to learn distributions in a systematic way over parse trees. Okay, so I think this was all meant to motivate the importance of the box and what you can do with this box. The question now is, we focus on the input, let's look at the output. What do we do? What do we generate as a model in this particular case? So the next story has two components. The one is purely logical, in which we will take these constraints that define our structured space and put them in a form that make that structured space tractable. And I'll tell you particularly what do we mean by tractable. And then we're going to induce a distribution over that structured space, which is going to eventually be learned from data, right? So here's the first part. We're going to take the constraints and convert them into a circuit. This circuit corresponds to the running example that I have from the beginning. The simplest property that it has, it captures the structure space in the simple sense that you expect. If you give me a point, you evaluate the circuit. If it gives you a 1, that means that variable instantiation is in the structured space. If it evaluates to 0, it is not. However, this circuit must satisfy some additional requirements that allow you to do tractable reasoning on that structure space, including inducing a distribution and computing marginal probabilities all in linear time. So the next 3 slides will tell you what these 3 properties are, and then we start adding numbers and we get to machine learning and probabilistic reasoning. So, but I can tell you upfront right now, these 3 properties I'm going to give you will enable the following things to be done in tractable time. The first question is, if I ask you, is this structured space that's encoded by this Boolean circuit, is it empty or non-empty? That happens to be SAT. That's empty complete. The first property I'm going to add to this will make that actually doable in linear time on this circuit. The second question is, how many members in the structured space? I want you to count them.
How many what?
How many elements in the structured space? Counting, Sharpie complete. The second property I'm going to put will make that linear as well. In fact, that gives you probabilistic reasoning immediately. Once you have these 2 properties. That's why it explains what we can do. But actually, I'm going to add one more, which allows us to even do learning in closed form when the data is complete. Folks, the secrets to the properties you're going to see on the probabilistic side and machine learning side are symbolic. And on this Boolean circuit, this is very important, right? The secret to tractability is symbolic. So what's the first property? Very simple. It's called decomposability. It says, if you look at every AND gate and you see the sub-circuits feeding into that gate, they don't overlap. No variables in common. That's it. You have decomposability. You can do SAT on this guy in linear time. It's simply a pass upward. You can imagine that because there's no interaction. Okay. So what gives you counting? So if this is a property on AND gates, you get counting by imposing a property on OR gates. And the property is called determinism. By the way, these 2 are old properties that I introduced a while back. It says, for any input that you evaluate the circuit at, no OR gate will have more than high input. So if you look at this guy, this is one particular evaluation on every variable being high. You look at this OR gate, low, high, low, low, high, low. You cannot have more than 1 high input for any circuit.
For any OR gate?
For any OR gate, right? That allows you basically count. Once you have this with decomposability, now you can count in linear time on these circuits. You can imagine it's like alpha or beta. Alpha or beta can never be true at the same time. So it's kind of mutual exclusiveness on ORs.
It's an everyday notion of
every OR. Yes. So, in fact, these two properties are pretty old, and we're going to have one more. And the third property, which gives us, we're done basically, we're going to start putting numbers now and do learning, leads to circuits that we call sentential decision diagrams. I introduced these about 5 years ago, and the reason for the name is they generalize binary decision diagrams. But if you look carefully, so what this gives you is a specialized version of decomposability and a specialized version of determinism. But if you look at these circuits, look at this structure. It's kind of recurrent. People who've done digital logic, it is kind of a selector structure. These circuits have this recurrent structure of a bunch of ANDs feeding into an OR. The ANDs have two inputs, and the requirement is on these circuits is for any circuit input, precisely one of these guys is high. Now, this is more specific. Precisely one of these guys is high. So basically, this fragment is selecting one of these wires as the output of that. It's a specialized version of determinism. What it gives you is, now I can do more than counting. If you give me two circuits and you ask me, do they represent the same structured space? I can do this now in polynomial time. Equivalence testing, all right? So with this additional property. So the other thing I have to say before I forget, in this whole approach, the computational bottleneck is in getting these circuits. That is, in taking a Boolean expression that characterizes your structured space and getting a circuit that has these properties. If you manage, you're in heaven, as you'll see, because everything from there on is basically linear, 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 okay? This is what I just said, right? You get these things, and by the way, decomposability and determinism, they're old. I introduced these about more than a decade ago in a JCM paper, and they've been recently adopted by Toyota. If you've configured a car during the last year with either Toyota or Lexus, you've had one of these circuits into your web browser. They're used for configuration, online configuration. There was a news release on this last spring by UCLA. Okay, now we get to the fun part. All of this is about characterizing the structured space in a way that allows me to do certain things with it easily. The main thing I want to do is induce a distribution over it. And the way we do this is by simply putting distributions on the local distributions on the inputs of OR gates. Now we have something called the probabilistic SDD, and I'll show you now the semantics. This is now a distribution over the structured space encoded by the circuit. What is that distribution? It's pretty simple. You give me an instantiation, you evaluate the circuit. If the circuit evaluates to 0, that means outside the space, 0 probability. But if it is inside the space, you're going to get a high. All I have to show you is what is the probability of that instantiation, and then we're done with the semantics. It's pretty simple. You trace the high wire all the way down and multiply the numbers that you encounter. All right, so the probability of this guy is this. Okay, here's the first surprising result.
Sorry, I didn't understand. So what is this modeling now? So
I'm giving you the semantics. I'm telling you that this creature, we understood what the Boolean circuit is. It characterizes a structured space. I'm putting a distribution on the structured space.
On the structure space.
So assigning a number for every element in the structured space. And I'm going to do it like this. By simply assigning local distributions on OR gates. Now you're going to say, wait a minute, so how does this induce a distribution over the elements of that space? And I'm showing you how. Let me just do this once more, and I'll answer you, Russ. You bring a variable instantiation, and you say, according to this creature, what is the probability of that instantiation, right? And I tell you, OK, we'll evaluate the Boolean circuit. If I get a 0, that point is outside the space, probability 0. If I get a high, like in this case, that's inside the structured space. And now I'm going to tell you how to get the probability of that. You trace the red wire all the way, and you multiply all numbers you encounter along the way. So in this case, it's 0.3 by 0.1, 0.8, 0.4, 0.25. And that's the property of this element.
Red is 0?
What is it?
Red is 0?
Red is high.
But is it kind of similar to, a lot of people are looking at these probabilistic trees.
Right.
So these are graphs in general, not trees. They're drawn like this for visual clarity, but if you actually avoid sharing, so there is P and not P, okay, if you actually do not do the separation, these are graphs, not trees. They're real circuits. But let me just say one thing, which is surprising. This guy is normalized. Even though when we assign the numbers, we enforce no global condition on the numbers. We just ensure that they're locally normalized for each OR gate. The semantics that I just gave you lead to a distribution that's normalized. In fact, I'll show you more surprising properties about this representation. One of them is this guy satisfies conditional independence properties that can be read off from the Boolean circuit structure. There is a couple of theorems in the original paper that says, you look at the Boolean circuit structure and you identify alpha, beta, gamma, a whole class of them, and this distribution is guaranteed to find alpha independent of beta given gamma, regardless of how you parameterize it. Just like in Bayesian networks, the topology, or in Markov networks, the topology forces independence constraints on the global distribution, regardless of how you parameterize. The biggest difference, though, is in these graphical models, the independence is what we call variable-based. I is independent of j given k. In this particular case, the independence is sentence-based, Boolean expression-based. So it's more refined, all right? So this is the distribution that's induced, it's normalized, and inference on this distribution can be done in linear time for both finding the most likely instantiation for computing marginals over variables given evidence. In fact, the algorithm are similar to backprop. You give me evidence, I set it as input, I do one pass, I get the probability of that evidence. I do a second pass backward differentiating, and the derivatives gives the marginals for the different quantities that I want. So it's actually pretty well-behaved. Now, but I want to learn these things. So typically what you do is you give me the specification as a Boolean sentence, and you give me data, and I want to learn the numbers from data. So that's what I'm going to get to next. But let me just make one more remark. Again, a while back, I introduced these arithmetic circuit representations of distributions as a tractable way of representing distribution in JCM. These guys are arithmetic circuits. You can just unfold them in a very standard way, and you get arithmetic circuits, but that satisfy stronger properties than those that I identified a while back. So you can think of these guys, the PSDDs, as the new generation of arithmetic circuits over structured spaces. And you may have been exposed to these under the name of SPNs. They're studied under the name sum product networks in the machine learning literature now. Okay, now we get to the learning part. Well, the results on learning are surprising, but I'm going to give you a main result theorem that tells you why. Why do we get these nice things? The bottom line is maximum likelihood parameters are unique. You can get them in closed form. But I'm going to show you an underlying theorem that gives you the insight of why that happens, which is this. These parameters are interpretable in the following way. Look at the subcircuit here. Forget the numbers. Just look at this subcircuit. It actually simplifies to the student took course L. Look at this subcircuit here. It says the student took course P. Let's look at this number here. Now, these two circuits are related to this number in a very specific way. Under this circuit, I will select this part. Under this circuit, I will select that. So if you go back to the selector semantic, guaranteed. The probability of P given L in the global distribution induced by this circuit must be 0.4.
Must be?
0.4. And this is invariant to any change you make in the circuit. You can change any number in the circuit, and you're guaranteed in the global distribution induced by the circuit, the probability of P given L is 0.4. Just like in Bayesian networks, which is people who are familiar with this realize how hard it is to get this property. You don't get this, for example, in Markov networks because of normalization. These numbers are interpretable They have particular semantics. And because of this, by the way, this program was mentioned this morning. We're also excited to be part of it. It's coming up later in May. Because of this, you can do closed form estimation of parameters under complete data. Really, it amounts to this. You initialize all of your parameters to 0. You walk through your data set. You take each line in the data set, you evaluate the circuit, and start incrementing the wires when they're on or not. And you normalize at the end. That's basically the algorithm. And you get maximum likelihood parameters. We have an algorithm, EM algorithm, also for incomplete data that I'm going to show you some results about later. But let me ask you a question. That's parameter estimation. What is the structured learning problem in this case? Anytime you have a graphical model like this, people talk about either learning the structure or learning the parameters. So I told you about learning parameters. What is learning structure in this case?
Similar to some product networks, it's just basically figuring out where to put things and how to break things.
No, but I have a Boolean circuit that defines the structure of the PSDD.
You haven't told us how to learn that circuit, actually.
Exactly. Good. Aha. You don't have to learn it. You compile it from the constraints, but there are multiple Boolean circuits that satisfy the properties that I told you. And the structured learning problem is which one of these do you choose? Because which circuit you choose defines your parameter space, and then you're doing the learning. Now, here's the surprising thing, and I'll end this talk by telling you about an insight on that. We have only been using the naive way of learning this circuit by trying to minimize its size. Anybody who does learning knows that this is not a good idea. Actually, it worked pretty well. And one of the puzzling things has been in our group, why are we getting away with only minimizing the size of the Boolean circuit as opposed to doing anything more sophisticated like balancing and regular? Right, okay, I'll tell you, it's not published, but I'll end with one remark on that. It's pretty interesting. So far we're only doing naive, try to compile circuits that minimize the size. How do you do that? You go to some of the logic libraries. We have a library online called the SDD library, which does precisely that, right? It basically compiles these things and try to minimize their size. It's a heavy duty based on SAT technology, similar to what you'd find about compiling into binary decision diagrams and so on, same kind of space and technology, all right? We're now doing more sophisticated structured learning, and that should be coming out soon. Okay, I'm almost done. I'm gonna show you some experimental results and tell you about what else this allows you to do, in particular new types of data sets that have been missed in the machine learning literature as far as I'm concerned. So first, comparing this naive learning approach with the mallows, right, on learning distributions over permutations. On one of the classical data sets out there. We use the box by Boutillier. The mallows does not compete with this. The mallows is unimodal, and we had to go into 20 mixtures of the mallows to start getting comparable results to what we have. This is remarkable on two counts. One, our box knows nothing about permutation except those constraints that I showed you. That's it.
But they characterize permutations.
What is it?
But they characterize the permutations.
They characterize permutations, yes, but there was no thinking in developing the box that relates to permutations except writing these constraints. And it's doing this well, and we're just minimizing the size of the circuit. But I have an explanation for that at the end, why minimizing the size of the circuit seems to be okay. We've also tried experiments of what happens when you ignore constraints, because that's what people tend to do usually. They just ignore the constraints. In this case, we had graphical models, Bayesian networks synthesized from relational models. They're large. They have a lot of zeros on them. We converted the zeros to these constraints. We simulated data from those. And in fact, we tried SPNs and arithmetic circuits that are not over structure spaces. We gave them just the data. And we gave our box both the data and the constraints. And you can see what's going on, which is what you expect. It's much worse when you don't have enough data, if you don't know about the constraints. As the data grows, you start catching up, right? Because you start figuring out that, but still, you don't catch up, right? So this is PSDDs learning from both data and constraints. This is other type of models, circuits in particular, not knowing about the constraints. We've used this also for doing distributions over game outputs. Let's say you're playing a game, and you want to induce a distribution over the outcomes of the game. How do you do it? Unless someone studied that game, you're on your own. You have to come up with models for that. In this case, you just write the outputs of the game are a structured probability space. You come up with your Boolean constraints, you write the expressions, and you induce that. We did it for few types of games. In fact, in this case, this is a cool idea. We integrated this with Naïve Bayes classification. The idea is I have a classical Naïve Bayes, but each one of these attributes is a structured space, all possible outcomes of a game. So if you, and I want to use it to tell you, oh, these two players played 5 games, and here's the output of the 5 games. What's the first player? Are they optimal, heuristic, or random? Naïve Bayes classifier, you just go and assert the values of the games here and compute the posterior. The problem is each one of these guys now have a structured space. What do? Very simple. In a Naïve Bayes classifier, you have a distribution over this guy 3 numbers. And for each one of these variables, you need a distribution given C. That's 3 distributions, 3 PSDDs, which you learn in the standard way in Naïve Bayes. It's a powerful idea. So now you can do Naïve Bayes where the features themselves are members of a structured space. Right? We do this.
I'm not sure what that means, sorry.
Yes.
So a feature is some...
Usually feature is color.
Yeah, but here it's not a number.
It is a combinatorial object.
Yes.
That could be a game outcome or. Yes?
No, but what's the output of the classifier?
When you come and bring me 3 outputs of a game, the output of the classifier is what's the most likely type of the player?
One of those 3 things.
One of these 3. But the point is I can now do Naïve Bayes classification where the features themselves are coming from a structured space. Nothing fancy here. It's just putting this idea together with Naïve Bayes classification. Right. There's nothing technical big here. The point is, you build a Naïve Bayes classifier where you quantify X given C using a PSDD, using a distribution over a structured spaces. There's no theorem here. Okay, let me conclude with this, because that's actually interesting. In machine learning, when people talk about data sets, they say complete and incomplete data set. This is what they mean by complete, right? You have 3 variables, let's say, and every row in the data is a full instantiation, gives you the value of every variable. And when they say, I have incomplete data, they mean this. Some of these guys are missing. What does that mean? That means I cannot fully describe example 1. All I can tell you about it is the value of X is this, the value of Y, and I don't know the value of Z. But in logic, what this means is I'm describing it using what we call a term. But why do I have to restrict to that? I may see an example. I want to describe it in a more general way. I want to use an arbitrary Boolean expression to tell you what I know about that example. Why do I have to just restrict it to saying, I know the value of these variables and not that? There's no difference. Do you see these in the literature? I'll tell you why you don't see them. OK, we can handle this in this framework. To handle these, you have to have some kind of an incomplete algorithm like EM. To build an algorithm for EM, for these or those, you will need to condition your distribution on the partial descriptions of examples. Conditioning on a partial variable instantiation is bread and butter in machine learning and all of the classical algorithms you see, whether they are approximate or exact. Conditioning on an arbitrary Boolean expression is not part of the repertoire that people have. You can do this. There's nothing conceptually different. You just have to know how to efficiently condition on arbitrary Boolean expressions. In this framework, if you can take this Boolean expression and compile it into a circuit that's compatible with the original master circuit in a certain way, you can condition in quadratic time. So you can do this efficiently, regardless of the Boolean expression, as long as you get a circuit for it. And these example descriptions are usually simple. the compilation process is easy. It's not like the original constraints. So actually, the final results I'm going to report on use this. Okay, you're going to tell me, why did you use this? Okay, permutations. If I say complete data, I'm asking every user to give me the position of every item. So in number 1 is this type of sushi, number 2 is this type of sushi. The classical incomplete, I'm allowing them to say, okay, I'll tell you what's first and what's second, but I'm not going to tell you what's third, right? With this, they can tell you anything. They can say, I like this better than that, and this better than that. Or this is first, and this is greater than that. Anything, any Boolean expression. Pretty powerful, right? But again, the key is to know how to condition on arbitrary Boolean expressions. Okay, the same idea can be used, and this last case study, I'll give you the references later. We did a structured space that corresponds to tiers, partial rankings, so not total rankings. You could have like 5 tiers, and items can belong into one of them. And we use this in one of the data sets for movie lens. And the idea is eventually, I give you a user, and I tell you I know the following about them. Make the top 5 recommendations based on expected tier. And you get this. Classical task in this area is what people call diversified recommendations. I want to be able to come and tell you, can you give me the top 5 so that there's no other Star Wars movie and there's at least one comedy? Dedicated approaches for this in the recommender literature. Not here. You just write a Boolean expression. This amounts to conditioning your distribution on a Boolean expression that captures that and computing the probability of a Boolean expression. As long as the condition and the query are compilable to circuits that are compatible with the original circuit, done.
But what's the
Polynomial.
original circuit?
What is it?
What's the original circuit?
The original circuit is the one I got by compiling the structured space corresponding to tiers. I didn't show you that. Just like in permutations, I wrote the constraints that capture the permutation space. We have an encoding that captures the structured space of tiers. I didn't go over it. It's in the paper. It's another structured space. And I got a circuit for that, and I learned the numbers on it. And that's now a distribution over items in tiers. Yet another distribution over another type of combinatorial object.
But what's the ranking using?
It is using the expected place in a tier. So there's tier 1, tier 2, tier 3. So it's expected tier, right, for this one. But for the permutation, it would be the expected position and so on. Linear time. All of this can be computed in linear time in the output circuit that you have. All right, so I'm basically done. Structured spaces everywhere. People deal with them in all kinds of ways, from ignoring them to handcrafting them into model to and so on. You've seen examples. Well, we just provided one systematic way of dealing with them and inducing tractable distributions over them. And I think in the process, yesterday we were talking about symbolic logic and symbolic reasoning. You've seen where it actually plays a role in specifying the structured space, in specifying structured data sets, and in specifying structured queries. The main output of that is this PSDD representation. Let me just end with this remark. The fact that we were only minimizing the sizes of the circuits, not doing anything more sophisticated for structured learning. I've been telling my group what's going on. It's a bit surprising. We now have an interpretation. It's not published, but I can tell you this. You can interpret the circuit as doing a recursive matrix decomposition over the structured space. You can interpret the space itself as a matrix, big matrix. The rows are the members of the space. You can go to every wire in the circuit and interpret it as a matrix, where what you're doing is circuit matrix operations until you get the bigger matrix out there. And under this interpretation, you can actually assign feature interpretation to elements of the circuit. So actually, when you're taking your structured space and getting one of these circuits, You are doing recursive matrix decomposition, and you're, in a sense, identifying features. I just wanted to add with this. That's unpublished, but I sleep a little bit better now with this interpretation. Thank you. Oh, and